proportional to the derivative of n over 2, where n is the dimension of the manifold, well, that this is some local part, this is the non-local part, and in odd dimension it's just equal to that n over 2. When n is odd, then n over 2 is not an integer, that's why this is a new global invariant that gives you the logarithmic determinant. Okay, so now back to the relativistic heat rate. The trick is this formula that can express heat semigroup of the pseudo-differential operator omega, the heat semigroup of the differential operator h. And once you have this, you take trace of both sides, you get this equation. And this is known. This is the well-known static classical heat trace. And this is the new one. So now for this, I introduce the Newlin-Bars representation, take the integral over t, and I get a new formula, new representation for the relativistic heat trace in terms of this contour integral. Recall that this AQ is an entire function. And these have some poles, these are meromorphic functions. And now by taking this contour and moving it to the right, I get the asymptotic expansion of the this just by doing the residue, just calculating this integral by the residue theorem. So what you get is the poles of this gamma function give you the a at the integer points, and that will be the local part. The poles of this gamma function will give you the values of a at the other points, and that will give you the non-local invariant. So in other words, the asymptotic expansion looks like this. There is a local part and there is a non-local part. So this is the high temperature expansion of this invariant. So the non-local part for even dimension is expressed in terms of the values of these coefficients at the half integer points, and the non-dimension in terms of the derivatives of the integer points. And the additional part is that there is a logarithm term in the asymptotic expansion, which was absent in the classical case. Well, similar idea can be used to deal with the quantum heat traces. You could express this function in terms, again, of classical heat semigroup by using this integral, where these are some function given by this formula, and these are interesting functions that can be studied, but I don't have time to talk about this. And then if you take the trace, you get this quantum heat traces expressed in terms of the classical heat trace, and doing it, representing this in terms of the Newlin-Bars integral, you put it back, you integrate over t, and then gives you this new formula. This is exact formula. And then again, if you take this contour and move it to the right, you're hitting those poles coming from these two gamma functions. And by the way, this function f, they are given by this series, and these are interesting functions. Well, let me just mention that for mu equals 0, for chemical potential equals 0, they're determined by the Riemann-Zeta function. And this one, the bosonic part is meromorphic with the pole, and the fermionic part is entire, doesn't have any pole. So, and then by the same trick, you get this asymptotic expansion of quantum heat traces. There is a local part and there is a non-local part. The local part looks like this with some numerical coefficients that I made. I don't want to talk about them. But they are expressed in terms of, you see that there are these beta to negative n, that's the leading part. And then there are the non-local part is expressed by the values of this, the half integer point, the derivatives, and the logarithms. And for the zero chemical potential, there is an additional, well, difficulty. You need to modify the contour and do a little bit more careful, but then you get the local part looking like this, and it kind of terminates in for high K. This for fermionic case, because of some Riemann-Zeta function vanishes at negative points, then it terminates that this is just finite series. And for the non-local part, it looks like this. There are in even dimension looks like that, in odd dimension looks like this. And in bosonic case, there is an extra singular term that is proportional to 1 over beta and proportional to this new invariant. Again, n is the